Thank you very much for the introduction, and thank you everyone for, well, resisting until the very last. So the last talk will be kind of a very relaxed, laid-back walkthrough on a little bit of a different perspective in terms of statistics and application of statistics to the topic of uncertainty quantification and one particular subtopic which is called reliability analysis from the engineering perspective. So it's kind of a difference. I'm kind of the black sheep here, because I represent the chair of risk, safety, and uncertainty quantification in ETH Zurich, which deals with carrying out research in the field of uncertainty quantification for engineering problems with application to structural reliability, sensitivity analysis, we just had an excellent talk from Olivier, model calibration, which is related to Bayesian inversion, reliability-based design optimization, and so on and so forth. The chair is led by Professor Bruno Soudret. And I apologize, I see that the colors are somewhat weird, so I hope the images will come out nice anyway towards the end, because I have nice animations. So, we do research on a number of topics, and today I will be actually introducing two of them. One of them is metamodels, and the other one, or surrogate models, and the other one is structural reliability analysis. Okay? So, just to give acknowledgement where it's due, this lecture is largely based on three courses that we teach in ETH Zurich. One is uncertainty quantification engineering, the other one is structural reliability and risk analysis, and the third one is actually a block course in a joint venture with the University of Zurich, which is called uncertainty quantification and data analysis in applied sciences, and we teach the first block. Everything is taught by Professor Soudret and myself. So, that said, the outline of my talk, in the very first part, I will try to kind of set a common jargon, because we come from different backgrounds, and so we need to kind of understand each other. Then I will introduce one particular type of tools that we use, which is called Gaussian process modeling. And then we will see how to use these objects within a particular type of application, which is called reliability analysis, and then how to use it in a, let's say, more advanced way. And then I will draw some conclusions. Okay? So, let's start with the terminology, okay? So we're all familiar with computational models. And what are computational models in engineering fields, okay? So they're also called simulators. Actually, most often people talk about simulations or simulators when talking about computational models. And what they are, they're basically a combination of what you're very good at, which is the mathematical description, of what? Of reality, okay? Of something that has to do with some physical process, okay? And then some discretization techniques to basically go from continuous to discrete algebra that you can actually solve, and some algorithm to smartly solve them, okay? Now, how do we use them? Well, basically there are a number of ways to use them, and from basically try to calibrate them from real data, such then we can create what are called virtual prototypes, which are basically cheaper than just building 100 of cars, and then throw each one of them against the wall. We can maybe try to calibrate by using some cars. We can try to build some type of finite element model of the car and then make a simulation, because that's actually cheaper than destroying the car. You would be surprised how few cars are destroyed in an actual, from zero to the final design of the car. We're talking about 5 or 6. And we're talking then about millions of cars out there. Then they're used to optimize the system. So as an example, why you have to reduce cost and within performance constraints. And you can use them to assess the robustness, reliability. Will this building fall in case of an earthquake? Will it not? And so on and so forth. However, remarks, what's one of the characteristics? They are expensive. So a real engineering model doesn't take less than 1 hour to run, even on dedicated infrastructure, okay? And another very big thing is they're very often proprietary. They're bought from someone else. There's no source code. We have no idea about the equations that are solved inside. So they're completely black boxes. We can run them on a certain set of parameters. We can get the response of the model. We don't know how we get there, or most of the times we don't. But then we have an issue, because the real world is actually uncertain. So even just when you have your design, your beautiful Tesla design on your computer, and you want to throw out in the road, and then you order the pieces from the manufacturer, and they're actually all different than one another, and all different than what you requested. Sometimes it's actually even a property of materials themselves. As an example, you're talking about concrete, and well, depending on the day the concrete was mixed, the properties change. But then you're also talking about unforecast exposure, so you're also talking about the loads that the systems will be subject to. So as an example, due to, well, extreme events, floods, earthquakes, hurricanes, or anything, accidental human action, but also terror. So we have to keep all of them in mind, basically, when dealing with those very highly expensive systems. So how do we deal with this in a quantitative sense? Okay, so there is uncertainty. We need to take care of uncertainty. So what I'm showing here is basically, it's a framework. It's kind of a mindset. So this will set some semantics that I will use later on, so that we always know what we are talking about. So we've talked about physical models, and that we all agree, basically they are, well, whatever computational model you're working on, could be PDEs, finite element models, finite differences, whatever type of integration technique you want to use. Those models typically depend on a number of parameters and or boundary conditions, okay? But those boundary conditions are subject to uncertainty. As I just said, that could be due to, well, practical or physical reasons, but it could be due to lack of knowledge, as we saw in an earlier talk. And for the sake of today, I only have 1 hour to talk about basically the contents of 3 courses, so bear with me if I will tell you, let's only consider those particular sources of uncertainty for today that can be represented through random variables, okay? You have a number of parameters or boundary conditions, and they can be put together through some type of random joint probability distribution. And then what's the idea? The randomness in this particular type of models, in particular type of input models, or models of uncertainty, when propagated through a physical model, which again, for the sake of today, we will consider deterministic, as opposite to what was just presented by Olivier, but otherwise I would need probably a couple more lectures. So the probabilistic input, once propagated through the deterministic model, results in actually, of course, a probabilistic output, a stochastic response. And with those things, we want to do something. With this particular output, we want to give some form of characterization, be it the moments, be it the probability of failure or not performing within nominal ranges, the response PDF, or whatever. Sometimes we want to do some types of analysis, as an example, sensitivity analysis that was just introduced, or even Bayesian calibration. And through this particular type of information, we can actually update our problem and rethink about the sources of uncertainty, as an example, to work in smaller dimension, which is typically easier than in higher dimension, or to actually have reduced variability ranges once you condition basically your initial information on data. So I will now focus throughout the lecture on the third step, which is uncertainty propagation. So it's really going from the uncertainty in the inputs that we give as granted. One whole field of UQ is actually figuring out the uncertainties. It's very important, but today let's imagine that we have a joint PDF of the inputs. And the idea, and the question is, I have a black box model, how do we get to the uncertainty onto the output? And what do I want to know? Well, if I'm lucky, just mean standard deviation. If I'm less lucky, response PDF. And sometimes if I'm really less lucky, I have to go to the probability of failure. And I will focus a little bit on these on the last part of the lecture, because it's a very interesting problem. So, what's the solution? Monte Carlo simulation. Monte Carlo simulation is very nice, because basically the methodology you know very well, so we'll kind of skip it. So you just make a big sample from the inputs that you assume known. You get the model responses, and you do whatever statistics you like. So this is great. It allows you to do anything that you like, but convergence, that's a big issue. Monte Carlo simulation requires a large number of samples to get meaningful estimates. And as I said, so the typical number of samples, we're talking about 10 to the 3 to 10 to the 6, and sometimes much higher. We'll see an example later. And just, that's not feasible. We have typically in engineering scenarios, we have a budget of maybe 100 runs. That's it. So, metamodels come in quite handy. So I will be using in a kind of interchangeable way the word metamodels and surrogate models, but I will introduce a little bit of a subtle difference between the two in a later part of the talk. So what is a metamodel? Well, the idea of a metamodel is some kind of inexpensive to evaluate, typically analytical function that approximate accurately with respect to some accuracy measure, a computational model, okay? And it is built from a small sample of point-wise evaluation. So I'm talking about a non-intrusive or black box approach to build the model. And this small experimental design, which could be, as an example, a Monte Carlo sample, but small, typically a few hundred points or 100 points, this is completely evaluated point by point through black boxes. We know nothing about how this thing comes out. And a couple of metamodeling techniques you probably have heard about. One of them is polynomial cost expansions that was just described by Olivier. And another one you may have heard about it is kriging, where instead of basically having a deterministic regression problem, you have basically, you present your model as something stochastic, and more on this in the next couple of slides. So that's more or less the setting, okay? We want to propagate uncertainty. Doing Monte Carlo would be perfect, but it's too expensive, so we try to use metamodels, okay? So what's the approach? Well, we do actually a small Monte Carlo, or something like this. If you're smarter, we can choose actually the points carefully. More on this maybe later. Then we calibrate the metamodel of choice in such a way that m tilde, which is the metamodel, in some sense behaves like the full model. And then we substitute the model with its surrogate, okay? And then we perform Monte Carlo sampling. Why do we do this? Because Monte Carlo sampling with the metamodel is inexpensive. We are talking about orders of millions or millions of model runs per second, okay? It's very, very cheap. They're polynomials or something like this per core. So what's the idea? The idea is we trade the computational cost of Monte Carlo, okay, which would be n Monte Carlo times n Monte Carlo runs, for the trade of for the cost of the experimental design, okay? So we ignore the cost of Monte Carlo now because doing it with surrogates is inexpensive, and however, we have to focus on the costs to calibrate the surrogate. So one very well-known tool for uncertainty quantification in general, and one very well-known metamodel is what is called Gaussian process modeling and or kriging. I will use the two words interchangeably. So I apologize for any one of you who know what the Gaussian process and what kriging is, but I have 1.5 slides to explain you Gaussian processes, so please bear with me. So the idea is, what is a Gaussian process, okay? Well, given that you have your own nice probability space with your sigma algebra and your probability measure, and you have some random variable or some random set of parameters that belongs to a space of dimensionality m, so m will be the dimensionality of our space, okay, the number of input parameters of your model. Then a stochastic process is basically a Gaussian stochastic process is such if basically for any finite sets of points that belong, or element that belong to R to the m, the joint distribution of z of this set of points is a Gaussian, okay? So it's basically an extension to infinite dimension of a random vector, okay, which is defined basically by the joint distribution of any random set of points, okay? Apologies to those of you who know what I'm talking about. So, a couple of notes. What is important about Gaussian processes is that they are entirely determined by two quantities. One of them is basically their mean, okay, which is a function of the input parameters x, okay, which is the expectation value of the random process, and by its covariance, okay. We know any joint distribution is a Gaussian variable, is a multivariate Gaussian variable. Basically, knowing those two types of information tells us everything that we need to know, completely characterize the process. Then the covariance function itself is normally, it's actually a positive definite kernel, which is in most cases, although it's not necessary, but it will make our life easier later on, usually stationary. So it's basically a kernel that only depends on some form of distance between the input points. And I will use a different notation later on because it makes stuff, again, simpler. If you rescale this object by removing the variance of the process, you get what is called the autocorrelation function. In the literature of kriging, this is very often used, autocorrelation rather than autocovariance. Or they're kind of, both of them are used. So just to see a Gaussian process in action in one dimension, by the way, they're also called Gaussian random fields. Some people may have heard them with this particular name. So consider this particular covariance kernel, okay, so it's basically, well, scaling times a Gaussian, okay, a multivariate Gaussian, independent, basically, with what are called scale parameters. So it's a parametric kernel. Oh, pardon, I forgot to put explicit dependence on theta here, but obviously there is a dependence on the theta vector, just scaling parameters for each one of the input variables. And consider that you have this object, and consider you have a 1D random field, and look at the effects of having a covariance kernel. So those are different realizations of the 1D version of this object for different values of theta I. And I'm sorry, this is not really visible. And you see that basically varying the theta changes the autocorrelation length, basically. And how does it translate on random realization? So we are talking about a random process, so there are trajectories. Those are several random processes generated, I think, with the same random field, with the same random seed. Maybe wrong, I don't remember, honestly. But for different values of theta, and as you see, basically having an autocovariance that decays very rapidly results in a relatively rough process, or realization. And having a very long covariance length, or a slowly decaying one, results in a very smooth process. Okay? So that's in a nutshell. Why are those nice? Because by tweaking some of the parameters, we can actually get some kind of continuous random variable which has properties of smoothness that can be somehow regulated. Okay? But so far, so good for Gaussian processes, but what's the use of Gaussian process? I mean, this object is just a random variable. It's not an emulator, it's not a metamodel, surrogate, nothing. So, and here comes the idea of kriging, okay? Also known as Gaussian process modeling, and in the machine learning community, Gaussian process regression. They're all related, basically, and sometimes they're exactly the same thing. So the idea is the following thing. Take our model, y equals m of x, okay? And for the sake of simplicity, again, y will be just a scalar value. So we are talking about a model which has scalar outputs, okay? Consider this is our model. Then we consider that our model is a realization, is a particular realization, this is very important, of this fancy random field, which is basically composed by one first part, which is a deterministic trend, okay, a regression trend, and then some scaling parameter times a stationary, zero mean, unit variance Gaussian process, okay? Where omega basically represents all this information that I said before, including basically the type of covariance that you are using and the parameters of the covariance kernel and so on and so forth, okay? Of course, there are regression coefficients, and this object is the variance of the Gaussian process. Now, one thing that I think that is very important, our model is one realization of this thing. That means that this particular Gaussian measure that we are introducing by using this machinery has nothing to do with the response of the actual model, okay? This is very important because it doesn't mean that we can only represent models whose output is actually Gaussian. So, let's take a couple of assumptions. So, now, we have a lot of, let's say, degree of freedom, and we have to make some assumptions to actually kind of choose meaningful Gaussian processes, and let's see. So historically, there are many approaches to how to make a trend. The simplest of them is basically considering that, well, we know there is no trend, basically. There is just a well-known constant. That's fine. We're happy with it. Ordinary basically tells you, OK, just try to grab the constant from the data. And universal kriging is basically put whatever you like as the trend of your model. And then the second assumption that we need to do, so this is an assumption, so at least the form of the trend we need to plug in, depending on our prior information, considerations on the nature of the model, or just basically random guess. And the second thing we have to choose is basically the type of autocorrelation function of the Gaussian process, of the unit variance stationary Gaussian process. And typically, you have to choose a family. I showed you earlier one particular family, which was the Gaussian family. There are many out there. They have fancy properties that can be interesting or less interesting. I will not dwell on these. We can discuss about that later. But the point is, we have to choose one form of this particular parametric covariance function. Okay? So, then what do? We start from some data. So I said metamodels, the idea is you train the cost of the Monte Carlo for the cost of the training. So we have some kind of set of training points, which I will call experimental design, and their number is NED, okay? It's this number which is expected to be much smaller than like the full Monte Carlo simulation you would like to run, but you can't afford. and the corresponding model responses, basically. I will always use this fancy notation with a parenthesis on top. That means I'm talking about points in the experimental design. Then we assume that the model is some realization of this particular random process that I described before, such that the values at the design points are known. So it's basically a condition. We are conditioning the random process to the particular data. And what's the goal? Remember, we want to use a metamodel. We want to approximate the model with this cheap approximation. So the goal is predict the value of our original model, okay, or to approximate the value of the original model in a new point, x0, that doesn't belong to the experimental design. Just as a mnemonic, I will put 0 I forgot the name. Basically, on the low part, yeah, as a subscript. Thanks. Sorry, as a subscript instead of a superscript, so that it's immediately apparent that it's not a point in the experimental design. So it's a very bad notation, but very quick when I only have an hour to describe the whole thing. So please bear with me if it's not very accurate. And this object must be something that I can use instead of the model to get the same information in a at least statistically coherent way that I would get from the full model. Okay, so we are looking for a predictor. So let's think about a bit about what is a Gaussian process. So we said a Gaussian process is that thing that is uniquely defined by the joint distribution of any set of basically on the joint distribution of its value on any set of point x. And this set of point could be the experimental design. Therefore, basically, if we have an experimental design, we know that the joint distribution, basically, what we know is that each one of the responses of the Gaussian random field, where this notation obviously, okay, I marked it here, means the Gaussian process on the experimental design point, it's a Gaussian variable with, it's very easy to demonstrate that it has this particular mean, and it can be entirely described by this very compact form, so it's a very nice linear linear model, given that we have z, which is now a standard random variable, and the joint distribution of any 2 points, so it's not very clear. Okay, no, it's clear, this is bold. So the joint distribution of any number of points, and this, I apologize, they should be removed, this index should be removed, is actually an NID joint Gaussian distribution with a certain mean and a certain covariance. Okay, so this is the response of the Gaussian process on the experimental design points. Okay, this allows us to define 2 ingredients, basically one which is called the regression matrix, which is basically just, well, the sum. It represents this part, basically, of the kriging process. It's a trend only. And then what is called the correlation matrix, which is basically what is derived from this correlation kernel or covariance kernel that we defined earlier. Okay? Now, the question is, okay, so far so good, but that's on the experimental design. So the question is, now we want to predict the next point, which is not in the experimental design. So what's the joint distribution? Well, it's the same game as before. The joint distribution is actually we want to predict a new point, so what will be the joint distribution between the new point and the point in the experimental design? Well, it will still be a Gaussian, but this time it has one more dimension, of course. It's because we are predicting 1 point. Obviously, if you have more points to predict, this object will become larger and larger Gaussian. And with the mean, which is just the mean as before, plus the value of the trend in the particular point y0, and covariance matrix, which is exactly like before. Let's look at the correlation part. You just add 1 on the main diagonal, and then you get the covariance, the cross correlation between the new points and all the other points in the experimental design. It's basically the same ingredients as before. Okay? So now we have a joint distribution. What do we do with this? We have the joint distribution of the experimental design plus this new point that we want to predict. So what do we do with this? Well, let's just take the mean predictor. With the Gaussian random field, it's a very logical choice because it's also the mode predictor, basically. It's also the most likely value. And well, it's a little bit of algebra, but very easy at the end of the day to get a linear predictor like this from the previous equation. So basically, the mean predictor, which is what we will use as the surrogate approximating the model, is given by this expression. Basically, there's a term which is basically just a trend plus a correction factor that is due to the Gaussian random field. And we'll see later what this does. This is a very important term. And then we can also get a variance out of this, because remember, we're talking about a Gaussian process. And okay, what we care about is the mean as the predictor, so this will be our surrogate model, that's good, but it's still a stochastic process, so it has a variance. So for each point, we can also have a look, we can also calculate explicitly in a closed form the variance for each new point. So, why is this interesting? The predictor has basically one term, which is a regression term, plus one term, which is basically a local correction, because that depends basically on where you are and on the covariance on the particular point you have. And one of the properties of those two things is that actually this particular surrogate interpolates experimental design. If you now throw inside here any point which is already in your experimental design, then the mean value will be exactly the value of your model, so it's an interpolator. And in addition, the variance of the process is 0. Again, for those of you who are familiar with Gaussian processes, I'm talking about models without noise, again, for the sake of time. So that's very nice. So we can predict the value on one point. It's consistent because if we try to predict the points we already know, we get exactly the same value with no variance. And how do we use this information? I'm very sorry, I don't know why the images look like this. They don't look like this on my screen, but probably if I turn it like this, you don't see it, so it won't help much. So due to this particular Gaussianity, we know for every point, basically the value, the mean. So if you could read the legend, you could see that basically in the blue line, this is an example of a 1D analytical function. And the yellow dots, believe me, there are yellow dots here, would be the points in the experimental design. And the dashed line would be the predictor, so this mean predictor that we just defined. So as you see, it interpolates through the data, and it kind of copies the behavior of the full function. And what you have in this gray area is actually the plus minus, I think, 1.96 sigma confidence level. So I'm just taking basically 95% confidence level for each point, considering that every point has a Gaussian distribution. So it's pretty easy to do. And the nice thing is the gradient predictor, of course, it's an interpolator. The more points you add, the more this object becomes, it's asymptotically consistent, so the whole variance tends to 0 everywhere, and the values tend to the actual value of the model. So we're happy. So far and so good, but we've only been talking about, I know everything about my Gaussian process, okay? But in practice, I don't know neither the actual parameters, given that I assume a certain covariance function. I don't know the parameters, I don't know the scaling factor, and I don't know the coefficients, okay? So the question is, in practice, what do I do? So I know that I need to solve Monte Carlo, I can't solve Monte Carlo, but I can run 100 runs. What can I do with those 100 runs, okay? So, well, I make a choice, as I said in the beginning, about a particular autocorrelation function. I like Gaussians, let's use a Gaussian autocorrelation function, or whatever that is. And then I try to estimate the parameters from the only data that I have, which are the experimental design points, okay? And how do I do this? Well, the cool thing is that everything here is Gaussian, so we can get a lot of stuff analytically, and what we can do is actually do maximum likelihood estimation to actually get the parameters of the theta parameters of the autocorrelation function and the corresponding beta and sigma squared. So just very quickly, I don't want to kill you. We have enough time, I guess. How do you do this? Well, you just use maximum likelihood estimation. Again, the likelihood is analytical, given all the Gaussianity everywhere. And I don't want to go through the solution, but just a couple of remarks, basically. What is cool about this particular expression is that solving for beta and sigma can be done separately than solving for theta, and I will in a minute explain why. But I want to give you a caveat. Again, I don't think you will be writing it down and developing in a couple of minutes, but once you introduce the estimation of beta from real data, so you're not given the beta, but you're estimating this from the data, then the variance of the Gaussian process changes slightly, okay? This is important because somehow the additional uncertainty you have due to the solution, due to the inference of the additional parameters is reflected in your predictor variance. So somehow the predictor becomes more uncertain, okay, due to the fact that you have to estimate additional parameters, okay? Let's say this is not very important if finding on any textbooks about kriging. But what is nice is that actually the log likelihood, if you see, it's quadratic in beta, and that's very nice because it has it's convex and it has a closed form solution. Very nice. It's basically generalized least squares. Super. And once we have beta, again, we can actually solve directly for sigma squared as well. And we have, again, an analytical expression, given that data are noiseless. Okay? Otherwise, this has to be estimated numerically from the data. But beta always admits the generalized least square solution. And then, basically, to get the correlation hyperparameters, you just have to solve with some method of your choice, global, local, anything, an optimization problem on the reduced likelihood function, basically, which is just basically the term that remains out of your whole thing. But for every value of theta, you can calculate sigma and you can calculate f, and so, well, it's basically just a matter of numerical optimization. Okay? So, let's see how do you use this. So, what do we do with all this machinery? Okay? Now we know, given a small sample, we know how to build an approximation to the full model. Okay? Using Gaussian processes. And how do we do this? I mean, let's try, basically. We see just a very, very easy, simple example, y equals x sin x. And our experimental design is basically 6 random points that are given us by someone who measured them, because why not? We've not been very lucky, as you can see, because there are some points are uniformly distributed all around. There is quite some information about your model, but there's not so much information about this region, because basically some of the points are clustered up together in one region. So, well, that's life. This is what we have to work with. So let's apply kriging. And well, this is the result of doing a kriging surrogate, given this particular data. I'm using a Gaussian kernel. In reality, I'm cheating. This would be a Matten kernel, but because in the previous slides I said Gaussian, I keep Gaussian here. And the optimization is just very simple gradient based. And as you can see, you see the following. So you see that in the experimental design points, your surrogate, which is the dashed line, perfectly interpolates. Okay? And when you are close to the experimental design points as expected, the kriging variance tends to 0. Why is this important? Okay? Well, to some degree, the kriging variance gives you information. And here comes the reason why I wrote metamodels everywhere instead of just surrogate models. Okay? The surrogate is one way to use this object, but the meta is some information which is not in the original model, which is the variance of the kriging model that you use to approximate it, can actually be used to learn something. And in particular, basically, this variance tells you something about how confident the surrogate is about its prediction, its own prediction. Okay? So it's actually pretty clear. When you are the points farthest from the experimental design, you have the maximum variance. The points closer to the experimental design, or where you have the most points, basically your conditioning of the Gaussian process is much stricter, so you have much smaller variability. So the question is, can we use this information? Okay? Can we do something better? So instead of just randomly, because we've been unlucky and someone gave us this kind of nice experimental design, let's say we have a budget of 10 model runs instead of just 6. How do we choose the next points? Okay, we start from this, how do we choose the next? Well, this brings us to kind of a keywords that are very, very popular nowadays, which is called active learning, which means, well, learning from my current status, knowledge status, okay? So the idea is I want to adaptively enrich experimental design in some regions of interest and capitalize on whatever information I have, okay? And there's a very naive approach for this, and given the status we were before, I'm producing here on the right, basically, the kriging variance, which is just the square of this particular, of this gray area. And obviously the most naive way is, okay, I take the place where there is the maximum variance, which is about 10, and I add it, okay, to the experimental design. Hello? Okay, nice. So I do it, and well, as you can expect, basically, let's see if the animations work. Okay, so the algorithm basically adds points always in the regions where there is maximum variance, and it basically targets those regions, and it enriches experimental design in such a way that our uncertainty, the epistemic uncertainty, is reduced everywhere. Note that this sampling is not necessarily uniform, not at all, because the more points you add, the better you condition the random field. And I don't have time to go into this discussion, but we can talk about this later. So let's now switch to the next step. So now we learned how to use kriging to approximate a full model and then to use it to do Monte Carlo simulation. One step back, why were we even doing this? And so the point is, what are the typical questions in engineering that kind of define the field of uncertainty quantification? And some of them are easy. What's the scattering of a quantity of interest, or basically of my model response? Another one is what was answered in the previous talk, which is, what are the parameters that drive the uncertainty in my model response? That was sensitivity analysis. Another one is, what's the probability of failure of my system? So what's the probability that my system doesn't perform where it should, or how it's supposed to be performing? What is the optimal design that minimizes the costs and still keeps performance to a certain degree? Or what are the, how can I reduce the uncertainty in my input, given that I have some observations of the output which are incomplete, basically, which is Bayesian inversion. In all this, we will be focusing on this particular problem now, probability of failure. Why? Because I introduced Monte Carlo, and Monte Carlo is very nice, and you've seen a lot of things about its convergence, and you're quite familiar with it. And probability of failure can result in one of the nastiest types of Monte Carlo around. Okay? So just very quickly, what is the limit state function? What is structural reliability or reliability analysis or rare event estimation, which is a close relative of set excursions, basically. This is various names depending on the community you talk to, basically. But it's always the same thing somehow. So the question is the following. If we define some type of failure criterion, okay, so which means my model performs fine as long as its response is below a certain threshold, okay? Whatever the response, whatever the model, and so on. But typical examples are, imagine you have a building, so you imagine you have a bridge, and basically if there is a lot of traffic, the bridge kind of bends a little bit, but it's fine as long as it doesn't bend 5 meters. If it bends 5 meters, the thing breaks down. So you can basically, based on your knowledge, you can define some type of threshold. And basically your question is, what's the probability given a certain model of the traffic that the displacement will be above the maximum admissible displacement? Or you can have a maximum temperature in a heat transfer problem. In an engine, temperature must not go above certain temperatures. Correct propagation, when you talk about nuclear safety, is extremely important, and so on and so forth. So how do we do it? We do it with a little trick, which is basically we define what is called the limit state function, or performance function, that probably to your eyes as mathematicians doesn't have any difference with what I defined in the beginning as a model. And it's right, but for engineering purposes, there is a big difference because the model relates to reality. This object is a function that is implicitly defined by its sign. It's a function that represents some condition of the system. So it could be, as an example, a combination of responses of different models. As an example, if you have really a bridge could be displacement in one point, it could be maximum stress on the cables in another point, so you can actually define it as kind of a sort of a combination of different models, or different physical models. And why is this interesting? It's interesting because it's defined basically by its sign. So this function must be smaller than 0 if the system is failing, smaller or equal to 0. It must be bigger than 0 if you're fine, if the system is performing in the nominal range, and, well, kind of the boundary of the two, which belongs to the failure region, is called limit state surface. In these particular cases, there's a very, very simple limit state function, which would be just basically the admissible threshold minus the model response. So if your model response is maximum temperature, and you have, so it's the temperature, maximum temperature in your system, and then you have a threshold of 100 degrees, and your model predicts 100 degrees, your objective function, your limit state function is basically, well, 100 degrees minus the actual temperature simulated, given the set of parameters you have. And it's usually represented in these fancy plots where you have kind of a failure domain in one region, a safe domain in the other, and the limit state surface in the middle. Okay? So what's the probability of failure? Well, the probability of failure is something very simple. It's a probability that given a certain input random vector x, okay? What's the probability that this particular, given this particular set of uncertainty or of uncertain input parameters, the response of the model will be in the failure domain. So the probability of failure is just defined basically as the integral of the input joint distribution in the domain of failure. Okay, it's nice, but we have an issue. It's a multidimensional input, and typically the dimension is order of 10 to 100 for an engineering system. And the domain of integration is actually implicit. That's the big issue, because it's defined through the limit state function. And what is more important is that failures are generally rare events. A very common failure has a probability of 10 to the minus 2. But a realistic, when you talk about nuclear safety or submarine safety, we have numbers in the order of 10 to the minus 6, 10 to the minus 7, so it could be very small. However, we'll see in a minute why this is important. We can reformulate the problem by using Monte Carlo simulation. We know Monte Carlo simulation, that's easy. So we can actually just define an indicator function, which basically is 1 if you are failing and 0 otherwise. And then the probability of failure is very simply the expectation value of this operator over the input domain. That's nice, because now we can use the entire input domain, which we know, and then we just, in the black box approach, we just need to know by value this particular function. So a very quick and dirty way to do this is to use Monte Carlo. Okay? Just take the expectation value of this particular indicator function. Okay? This is good, but I will probably skip this animation. So this is how you do it. You just sample, sample, sample. Some points will be failing, some points will not be failing, and the ratio of the number of points failing to the total dimension of your set is the probability of failure. Very easy. What's the issue? The issue is the following. This estimator is the sum of Bernoulli variables, okay? So it's basically, its distribution is a binomial distribution, which is nice, it's unbiased because it converges to the actual value, and it has convergence because the variance goes like 1 over n, but the issue is this part here. So 1 over n times pf or 1 minus pf. Why is this an issue? Because if you look at the coefficient of variation, so variance standard deviation divided by mean, well, for rare events, if pf is quite small, it tends to this particular value, 1 over square root of n, which we all know and love, times square root of pf. So what's the issue now? Well, consider that now we want to get an estimate of the probability of failure within 5%, okay? And we have a probability of failure of 10 to the minus k. The question is, how many Monte Carlo samples do we need to get this estimate right? And well, here is the issue. We need 4 times 10 to the k plus 2, which means basically even for a relatively failure-prone system, okay, 1% probability of failure, we need an order of 10 to the 4 runs, but we can only afford 100. That's where we have issues, okay? So, just one word more about reliability analysis. There is an entire course covering this. It's been studied for 40 years. There is a lot of research in how to deal with this problem in a number of different ways. What I want to present here, okay, so there are various families of methods. The idea of what I'm presenting here is just a very small subset where I am using plain Monte Carlo simulation, and I want to propose you a method based on metamodels plus active learning as a way, as a complementary way, which is complementary to all those, fancy other methods that are available, also all the methods that you've studied throughout this school, they can be put together to actually accelerate Monte Carlo, okay? So I just want to make sure that I'm showing kind of a very naive approach to the problem, but there's a lot of literature to do something a bit more advanced. So let's now use Kriging, okay? Step 1, we just use it, as I said in the beginning, we create a Kriging surrogate of some model of interest, in this particular case the limit state function, and we substitute it, and then we do Monte Carlo, okay? That's the very simplest way. So we calibrate Kriging on an experimental design, apologies, this is the wrong symbol, it would be capital NED, and we use the mean predictor as a substitute for the model, so we substitute basically to the domain of integration instead of G the mean of the Gaussian process, and then we calculate the probability of failure through Monte Carlo, exactly as we did before. And we can even set confidence levels due to the Kriging variance, basically. So we can basically define a conservative Kriging model where, remember, we are looking for values for which G is smaller than 0, okay? So if we want value for which G is smaller then zero, we want to be conservative. We take actually the mean predictor minus the variance. So it's more likely that you are in the failure region. Or the other way around if you want to get a non-conservative estimate. So we can kind of get confidence bounds, approximate confidence bounds on the estimate, our Monte Carlo estimate. And then we can do an estimation, pure Monte Carlo. You remember, it takes 1 second to make 1,000,000 runs. So we can do as many as we like. And we solve the problem 3 times, 1 time with the conservative estimate, 1 time with the optimistic estimate, and 1 time with just a substitution. And we can actually get 3 different probabilities of failure that are ordered like this. And basically we can say how confident we are with a particular estimate. Okay? Very simply, let's see an example of what is called the head function. It's called head function because there's the safe region down here, the failure region up here, and then the real limit state surface, which is the boundary between the two, resembles weakly a Mexican hat, with apologies to any Mexican in the audience. So we run it 100 times, as I said. So we just take a sampling of the input, we run it, and we have a reference solution, which is 1.07 by 10 to the minus 4. And what do we get? Well, look at the center first. So probability of failure, it's 4 by 10 to the minus 4. Not too bad. It's the same order of magnitude, and we spent 100 instead of what we would need, which is in the order of 1,000,000. But look at the confidence bounds. They are basically 4 orders of magnitude. We have an issue. Okay? So how do we improve on these? Of course, spoiler alert. What do we need? Okay? So as I said, we are looking for surrogates that are accurate in surrogating the model with respect to some appropriate accuracy measure. And now I come back to this statement. So now what's important when we look at the Monte Carlo estimates of PF? What's important is that the indicator function is correct, because that's what you use to calculate the Monte Carlo estimate. Therefore, what is important is actually the sign. Okay? What is important is that our surrogate has the same sign as G. We don't care if it looks weird, as long as it has the same sign. Okay? So can we actually use this particular information? So in other words, that means that it must classify properly the samples. So the question, can we do something? And that's of course yes. It's the same thing as we did before, active learning. But to do active learning, we need to define an enrichment criterion. What we did before was, well, we want to minimize the variance everywhere. That's a good enrichment criterion for let's say, for getting an overall model which behaves nicely everywhere. But in this case, we want to have an enrichment criterion that somehow is related to the sign, okay? That tells us where the model needs to be better constrained such that we don't get the wrong sign. And so what we do is we choose some enrichment criterion, we update the Kriging surrogate, we compute the probability of failure, and we get the bounds, and we check if the bounds are too wide or not too wide, and we decide whether we are satisfied with the results or not, okay? So again, I don't have time to go through all of these. There is a lot of literature. It's all recent literature. We're talking about research about the early 2000, actually 2005, 2010, basically, with the first real papers coming out around 2011. And a number of enrichment strategies have been proposed. But for the sake of time, I will be choosing the simplest, but very intuitive. You have a question? Oh, no, sorry. And most intuitive one, which is which is called learning function U. It's from a paper from Shading and not a paper from PhD from Esha. And well, it's actually a very, very simple function. Remember, what's our goal? Figuring out whether we have a good estimate of the sign of the function or not. And how do we do this? Well, let's now take basically this particular ratio. Remember, we can only use information that we already have at this current stage, okay? So we can only use the Gaussian process. We use the Gaussian process, and the information we have from the Gaussian process is the mean and the standard deviation. So let's have a look at this quantity. It's the absolute value of the mean divided by the standard deviation. In other words, it's the distance in terms of standard deviations from 0. Remember, what we are looking at is the sign of the function. So basically, this object has this nice property. Remember that for each point, the Gaussian predictor has a Gaussian distribution. So basically, this object tends to be large when you are very distant in terms of standard deviations from 0. which means that the probability that you get the wrong sign is very low, because you are at n sigma from, or actually u sigma from the 0, either from above or from below. On the other hand, this object tends to be very small when the mean is small, so you are close to 0, and the variance is large. So you are close to 0 indeed, and the variance is actually quite large. So you're really uncertain about the sign of your underlying function. So basically, choosing points where this is minimum yields the most information that we need in terms of improving our surrogate. We want to make sure that the surrogate everywhere has a high u, basically. It's always very well defined, okay? And by the way, due to Gaussianity, the probability of misclassification, so the probability of having either false positive or false negative, is really analytically given by the CDF of minus ux. That's just by definition, okay? I won't talk about this, but just very quickly, we have basically to choose the best point. Best means optimization. So how do we do it? Again, the u function is just a ratio between those two quantities. Again, you can get 1 million at a time. You don't really need to do anything fancy. You can do brute force Monte Carlo in most cases. Obviously, if you're in big dimension or you have complex problems, it's different. But for the sake of today, we take the same Monte Carlo points that we want to emulate, and we just get the point which is the minimum, okay? Let's see in one dimension. So this is the same function as before. I just translated it a little bit up so that it doesn't have 50% probability of being below 0. And we are interested basically in estimating the probability that the model is below 0. Basically, it's this area and this area divided by 15. Okay? Sorry, this area meaning this segment minus this segment divided by 15, which is the domain. Okay? So what's the first point that we look at? If you remember earlier, by just using active learning based on variance, the first point to add would be somewhere probably either like here or like here, because that's where the variance is the maximum. Experimental design is slightly different than before. But by using this particular u function, the most interesting point is actually this point here, which is very close to 0, and it has very high variability. It means that very likely the sign of my predictor here is wrong, okay? And indeed, you add that point to the experimental design, and because it's an interpolant, basically I'm really sorry that it's not very visible, the color, I did not expect this. The variance here is very reduced, so the next point, which is interest, you see the Kriging predictor goes to 0 around here, there is a certain amount of variance, and that's the next point. And you do it a few times, and well, very quickly you immediately explore the areas where there is uncertainty, and then basically at some point you stop. I'm not plotting here the convergence criterion. I will show you in the next slide, which comes by now. So I want to really conclude with a nice example, which is again just a toy example, because, well, we need to have a nice solution and to show in the lecture. But still, it's a nice example because it shows you what is known as a series system. So imagine you have a system with many components, and if any of the components fail, the system fails. And therefore, basically, each one of the components may have its own behavior depending on the boundary conditions and different and separate failure regions. And in this case, it's constructed by basically a set of simple polynomial functions. And what I want to show you is basically those 4 regions here, 1, 2, 3, and 4. So the input distributions are Gaussians. And those regions are actual failure regions, okay? And what we do is for each iteration, we add 1 point at a time. I don't have time to discuss about multiple point enrichment, but we add 1 point at a time, and we let the algorithm run until the bounds on PF. Okay, so remember the upper bound by taking the probability of failure using Kriging plus the variance, and the other one is Kriging minus the variance, actually the other way around. Gives us nested probabilities, and when the nested probabilities tend basically to collapse, we are converging. So we're presenting with a nice animation, last animation of today, where you have basically the initial starting experimental design, which are, I think, 12 points for unknown reason. On the top right, you have the learning function, basically. So this u function, the probability of misclassification. Here you have the current estimate of the probability of failure, so you will see some sort of convergence. And down right is the estimated boundary between the failure region and the safe region, and basically its conservative and its non-conservative estimate. So You start, and the first point that becomes interesting is basically somewhere, if you look at the U function, basically, given this particular experimental design, the current surrogate, you see that there are points which are very interesting either in this region or in this region, okay? Now you add the points, and what happens is now you added the point in this region, and now it's again interesting up here, and what happens is that now you start adding points, and you see that the algorithm starts enriching around the region that it knows. Then at some point, it becomes knowledgeable enough. It has become knowledgeable enough of this region, it has jumped to the next region. Because now here adding point doesn't add anything anymore, the variance is very small everywhere. So the other points become interesting. And then you start adding them here. After a while, you will start adding points here, and then here you see, unfortunately you don't see the confidence bounds, but you see the probability of failure starting to move and starting to converge. And down here you also see the actual estimated in green, it's the conservative estimate, so it's higher probability of failure, red is the non-conservative one. No, pardon, those are just, conservative and non-conservative ones. No, actually no, this is all just the zero, it's failure domain, pardon, and safe domain. And actually you let it run, and of course it discovers the other region, then it will discover the other region, and everyone lives happily ever after. With a total cost in terms of model runs, so we said this probability of failure is again order of 10 to the minus 4, and a total cost in terms of model run of basically 70, 80 runs, okay? And we calculated a probability of failure of 10 to the minus 4, which is very, very low. And we got it with extreme, you remember the confidence bounds, which are about 4 orders of magnitude. Why don't you allow me to click? Okay, you remember in the previous example, just by substitution, we had 4 orders of magnitude in the confidence bound. Here we are basically plus minus 5%. That's the thing. So with this, I am done. And instead of reading you the summary, which is basically what we just said, I just conclude with a remark. What I've presented you is basically very basic of many different techniques, but the idea was to walk you through a mindset on how to solve these problems. If you find this funny or interesting, there is a lot of literature about how to combine this fancy technique of active learning for a lot of different problems, from structural reliability by improving on the Monte Carlo estimate, so using subset sampling and all sorts of fancy hybrid sampling techniques, to actually using different surrogate models, so low-rank tensor approximations, PC Kriging, which have nicer exploration properties. So, this said, I hope I didn't make it too boring, and I'm done. So.
Okay, thank you very much for this interesting talk. Is there any questions?
Thank you for such an interesting talk. Just 2 questions I have. First, how does, like in the last examples that you showed, how would the computational time get affected by increasing the dimensionality of the problem? Like, does it blow up, or how?
So, this is a good question. So, the problem is to some degree the dimensionality of the problem. It depends on which ranges you're talking about. So, the predictor, the surrogate model, let's say, doesn't change. The cost increases slowly with the dimensionality of the problem. What changes the cost is the number of points in the experimental design. So the more points you have, the slower it becomes. But still remember that we are talking about models which are very expensive. So each iteration takes about a second to run in this particular setting, and we tested up to 20, 30 dimensions. Actually, we went up probably until 100 dimensions. And each iteration with the surrogate, excluding the time to run the model, takes at most a few seconds. So that's basically, we never reached yet the point where the computational costs to calculate the surrogate increase. The problem is that you have to be careful with which surrogate. So, and you really have to be careful because the curse of dimensionality affects everything, and in particular, it can affect surrogate models if you're not careful in designing sparse, basically, surrogates that take care of of the risk you have to get to the course of dimensionality. As an example, a piece expansion that was shown earlier by Olivier, the number of coefficients increases like binomial coefficients. It's huge. The more points, the more dimensions you have, you get exponentially, actually, factorial growth in the number of coefficients, and therefore in the costs for calibration and so on and so forth. So it's very difficult to reply to you in terms of what's the difference in time needed. It also depends on the topology of the limit state function. So if you have only one failure region, that's one thing. If you have disconnected, disjoint failure regions here and there, it can become more complicated. It also depends on the methods you're choosing. Here we're using Monte Carlo. It's very simple, very basic, but I have to run a million surrogate modeling evaluations per iteration. It takes a second or two. But you could use much faster ones, like subset simulation, where you only need to run thousands, as an example. So it's a layered question, and I can't give you a direct answer. Generally speaking, of course, it performs worse and worse the higher the dimension. But it's also the problem that it becomes tougher and tougher. So, yeah.
Thank you.
Other question?
I have two questions. The first one is, what happens if we insert uncertainty even in the barriers? So if we let the barrier stressed, so for example, if we...
This is very typical. The threshold is very typically a... So the point is your limit state function becomes the model minus the threshold, and the threshold is one random variable. That's very typical.
Okay.
So it's
it's
a typical setting.
this problem, this kind of problem.
Yeah, it's just a matter of defining G, the limit state function, in an appropriate way. This is one of the things I was saying at the beginning. I use two different symbols, even though in the end of the day they're both functions of the input, because M is very typical in engineering scenarios, refers to a physical model, a physical quantity that has an interpretation, while G is a function that can put together different models, including stochastic models of the resistance of your system, as an example, if the threshold is stochastic, and so on and so forth. So the easiest is you put the threshold to 0, and you just put M minus the threshold, and that's your G. Okay, where threshold is a threshold of random parameters as well. So you can always do this particular game. Or the threshold is a random parameter by itself.
Okay, and the second one is, what happens if we insert a different kind of dependency between, so you have stated that x and y are a Gaussian vector?
No,
in the first...
absolutely not.
No?
Wait. What do you call x and what do you call y? You mean x1 and x2?
And y is m of x is equal to m of x.
Y m of x, I don't know nothing about y. I don't know anything about the distribution. This is what I was saying with this big warning sign. Look,
okay.
having a Gaussian measure does not mean that y is Gaussian.
Okay.
So that's
that's fine. Okay.
Any other question? Actually, I have one question. Your system is pretty static, but what if your data is obtained from a time-dependent system? Does your method is straightforward?
So, no, there is a whole different layer of different problems. So you have to define the problem of reliability and of time-dependent reliability analysis. First, you have to define the problem. Given that you define the problem, then depending on how you define this problem, then you can either apply directly as it is, or depending on the definition, you have to change. So in particular, if you have models with multiple outputs, okay, and your limit state function is not as in this case, as an example, your model would have 4 different outputs, okay, because the model of your system has different subsystems, and you have 1 output per subsystem. You can also think about it as a time series, okay? If your problem is I have a time series and my system fails if any of the points fails, then you can almost straightforward define a limit state function, which is still a scalar, based on the output of your function. If your problem is more subtle, then it's the problem that needs to be defined. Okay. It's not a matter of technique, it's a matter of defining the problem. So again, sorry, I can't give you yes or no, but almost, let's say.
Yeah, thank you.
Probably.
So, can you go back to the slide just before the video? just before the video, can you go back to that slide? Where you had one-dimensional example.
Of what? Of active learning? Of
one-dimensional example of Kriging, like Gaussian
just
process?
Kriging, just the surrogate. Apologies, I'll get there.
Yes.
Like one, this one?
Yeah,
It's okay.
So my question is, if say you initially had an idea that the response function is convex.
No.
No, I'm saying that if say you already have an idea that the response function is going to be convex, but at one of the design points you got an error in your response, which led to, now since you are doing the way there's no variance at the design points, so now you'll always be stuck at non-convex.
I'm not sure really I understand your question. You're talking about this particular region of the model?
No, not this. So my question is, say you took a number of design points,
yes,
and you already have an idea that your response function is going to be convex. Say you already have an idea.
It's not this case. It's like I have prior knowledge that this is going to happen.
Yes.
Okay.
So you already have an idea. However, at one of the design points, you got some error in your response variable. Now, since there is no variance at any of your design points, because you are pretty much interpolating, so and that error led to non-convexivity in the interpolation.
But error, you mean an error like deviation from, like you have random noise on the simulation? Is that what you're talking about? Is that the error?
Yeah, I mean your response variable is such that whatever response you got, it's in a manner that it led to non-convexivity because of interpolation. Now, is there a way while you are doing your active learning to take care of that fact?
So, yeah, so just what I showed here is a very basic way of doing Kriging calibration, okay? In reality, there is the much more comprehensive set. The actual problem of calibrating Kriging can be cast as a Bayesian problem, okay? It's a Bayesian inverse problem. You need to find thetas. It's basically mapping, Bayesian mapping. And in Bayesian mapping, you can put a lot of additional information, including, as an example, information about monotonicity. You can put information about, random noise in the data, information about, as an example, convexity or non-convexity, information about anything that you may have, derivatives and all these. And you can build an appropriate setting in a Bayesian framework. Indeed, sometimes the calibration or the Gaussian, the Kriging, so the calibrated Gaussian process that you use, sometimes it's called the posterior process, because you can actually derive everything in a Bayesian way. So yes, it's possible. It's possible from these equations. No, not directly. Those equations make a lot of assumptions which are very basic. It's the basic thing I could do. But yes, it's possible. In theory, it's absolutely possible.
Okay. Is there any more questions? Let's thank the speaker again.